Good. Excellent.
Cool. I wasn't sure anyone was going to be here. Cool. So yeah, Keith sometimes has been coming.
Yeah, I saw that. That was awesome. Yeah, we're Dr. Greg gave us this actually really fun take home exam, but he gave us till tomorrow night to finish it. So probably some of us are. That's why I wasn't here and kind of forgot too.
Oh yeah, no. You're not obligated to be here at all.
No, I know that.
I
know,
do this so that I keep recording. So
absolutely, but
yeah.
I think it'll be really helpful for taking the qual.
Yeah, I also think it's going to be helpful for algebraic geometry. So that's
absolutely,
and that's another reason is I think like you guys need to see some extentor stuff. Yeah. Okay. So okay, maybe we should just go. So yeah, so I'm going to do some example computations. Oh, let's see. Should I make this bigger? Maybe a little bit bigger. Yeah. So example computations. Oh. All right.
You're recording also, right? I think I hit that button.
I think it's recording. It's got the little dot. And Tor. Okay, so I guess the first lemma that I want to do is the following. So let M and N be R modules. Okay, so the first thing that I want to say is that X0 RMN. So this is isomorphic to. So should I use HOM notation? Let's use HOM today. HOM RMN. And then 2 is that the Tor 0 of RMN. So this thing is isomorphic to M tensor over R with N. Okay, so let's do the proof. So for the first one, so we're going to let let I be an injective resolution. Of N. Okay, so then what we do is, so what does that mean? So that means we have an exact sequence like this. So this is an exact sequence where all those i's are, where all these i's are exact. And sometimes we think of it as a morphism of complexes, right? We think of this, I like to write it this way so that you don't mess up degrees, right? So we have it like this. So we can think of it like as a morphism of complexes. And the zeroth homology here, right? And the zeroth cohomology. So this thing is isomorphic to N. Okay, that's another way. So it's either an exact sequence like this, or you do take a complex, a more isomorphism of complexes where these are all injective, and then these have zero cohomology at all the other places, and then this, and then the 0th cohomology is isomorphic to n. Okay, so so to compute x, what we're going to do is we take the injective resolution. So we're going to apply HOM RM blank to the injective resolution to get a new complex, and this is the complex computing x, right? So so we have, oh, okay, sorry, I wrote this backwards. I wrote down a projective resolution, so I need to actually flip all the arrows here. Sorry.
I almost asked that. I apologize.
No. It's okay. It's okay. It's, So actually, all the arrows need to be flipped here.
I just saw that in your last video.
Yeah, and that would make sense too because the grading is all backwards. So I was like, why is this all going backwards? Okay. Okay, and then this arrow should be going the other way. All right. Okay, so this should be going the other way. Okay. And we still have this condition. This is the correct condition here. Okay. So we apply this to the injective resolution and we get a complex. Yeah, do you have another comment?
Yeah, just real quick. If n is itself injective, then the length of this thing is it just like 1 or 0 or?
Yeah, it's its own injective resolution, so it'll be of length 0. So I guess in that case, you just have I0, and that's also equal to n. Yeah.
Okay.
So it's its own resolution, and it's just a complex in degree 0, and that's it. Yeah.
Cool.
Yeah. So we have this. Okay. So now the numbers look better. Oh, what is going on with this? Okay. HOM R M I2. Okay. And then it keeps going. Okay, like this. And so this is the complex that we use to, so this isn't an exact sequence anymore, but this is the complex we use to compute x. By the way, we could have, if we did have a projective resolution here, we could have, like the way that I was writing the arrows originally, you'd write them with subscripts, and then you could compute x this way as well, right? But it would just flip everything around. Yeah, but you can compute them with projective resolutions too. So, okay, so we have this complex, and so what we're interested in computing is we're interested in computing H0, so X0 R of Mn is H0 of this complex, I bullet, like here. Okay, and so it's the kernel of this map. HOM R mod the image of the previous map. Okay, so the bottom is 0. So that's just the kernel. Okay, and so so I might have to restart the video to get rid of it if it keeps doing that. So this is the kernel of this thing. So this is really the kernel applied to I0 to I1, right? And so that's so this functor HM, which is this functor HOM M dash. So this is a representable functor. Representable. And so it preserves limits. Right? it's also the right adjoint of the tensor functor, right? So it's also a right adjoint. Of this functor, right? So in right adjoints preserve limits. And so you can either use that representable functors preserve limits or right adjoints preserve limits. Either way, it preserves limits, right? And so this is the kernel of, we have HM, we have I0 to HM of I1. And so since this preserves limits, this should be HM of the kernel of I0 to I1.
We talked about the kernel being a type of limit last semester. Right?
Exactly. The kernel is a type of limit. It's an equalizer between the zero map and the map that you have, right? Equalizers are limits, right? And so, yeah, and so this is and so this thing here, it means so yeah. So I just commuted the kernel in the functor because it preserves limits, and then we just talked about the kernel. So that's by this exactness here. So
is that pretty common to say to preserve means to commute?
Yeah. Yeah. That's the way we say it, right? So this is HM of n, or isomorphic to HM of n. And this is really Hom R of Mn. Okay, so we proved that x0 is Hom R of Mn. Right, so that's the proof of this one. Okay, so for the other one, it's going to be very similar, right? So let's do the part 2. Okay, so to prove the formula. For the second part, for Tor 0, let's take a projective resolution. And we can take either M or N. Let's do N again, I guess. N. Okay, so now we're going to have, so again, there's two ways of thinking about it. You can think of it as an exact sequence where these are all projectives. Right, or you can think of it as a morphism of complexes, right? So this is an exact sequence. And the PIs are projective. Okay, and then the complex really stops here. Okay, and so again, it's you can consider it as a morphism of complexes where the complex is graded, where the complex for n is just sitting in degree 0. Okay, and so now what we do is we apply the functor M R. So we're doing to the resolution. And again, you don't include the n part, right? So what do we get? So we get dot dot dot. Okay, so we have M tensor over R with P2, M tensor over R with P1, M tensor over R with P0, and then this goes to 0. Okay, so the Tor 0 is about this node. So we have the kernel mod the image is Tor 0. Okay, so all right, so the kernel mod the images is Tor 0. Okay. So so let me just kind of explicitly write that out. So the kernel of M tensor R P0 to 0 mod the image of M tensor R of P1 to M tensor R of P0. Okay, so this is what Tor 0 R of M n looks like. Okay. And so what is this thing here? So this thing is just the top thing, M tensor R of P0 modulo the image of M tensor R of P1 to M tensor R of P0. Okay, so let's give some of these things names. If I called this one F1, then this thing is M tensor F1, right? And what this thing we're really computing here is the co-kernel of M, this map here, the modified F1. Okay, but this is a colimit. Okay, and this in M tensor R is a left adjoint. Is a left adjoint. Adjoint. Left adjoints preserve colimits. Okay, so this thing's isomorphic to M tensor R, the co-kernel of F1. But what's the co-kernel of F1? Well, the co-kernel of F1 is this thing. So this is surjective, right? So this map here is surjective because the sequence is exact. And since the sequence is exact, it tells us that N is isomorphic to P0 mod F1 P1. Okay, so this is the co-kernel of F. Okay, and so that tells us here that this thing is isomorphic to M tensor R with N. Okay, so we're using just kind of the functorality, the properties that we get for free from the tensor products, right? From the functors, right? So here we have that this is left adjoints preserve colimits, and so you kind of get this thing here. And then on the other side, we used that it was a right adjoint, and right adjoints preserve limits, so we got the Halm on this side. So that was kind of the trick. All right, and so what did we prove? So we proved that this Tor here, right, is the same thing as this is just M tensor N. Okay. Okay, so let's dig into some computations.